Calculating TSA for solids with matching bases, Additive CSA. Welcome back, everyone. In our previous lesson, we explored the technique of decomposing complex, irregular solids into simpler, more manageable geometric shapes. Today, we are going to build on that foundation by focusing on a very specific and frequently encountered scenario in geometry. What happens when two or more of those individual solids are joined together at their flat bases to form a single, new object? We'll be looking at how this joining process changes the surface area we need to calculate. Understanding the concept of hidden surfaces. When you are calculating the total surface area, or TSA, of a single, standalone solid, your goal is to include every single face that is exposed to the outside. However, things change when we start joining two solids together. Think about what happens when you glue two flat faces together. Those faces don't disappear, but they do become internal boundaries. They are now trapped inside the object. This brings us to our fundamental rule, which you must memorize. Any surface that is covered or hidden during the joining process is no longer part of the exterior. Therefore, it must be excluded from your calculation of the combined object's TSA. To make this crystal clear, let's use a real-world analogy. Imagine you have two wooden discs. If they are separate, each disc has a top surface and a bottom surface that you can touch. But if you glue the bottom of the first disc directly to the top of the second disc, those two surfaces are now pressed against each other. They are no longer accessible, and more importantly, they are no longer paintable. Since you can't paint them, they can't be part of the surface area. Keep this in mind, because in the next slide, we will see how this logic allows us to use a much simpler method called Additive CSA to find our answer. Now that we've established that we are looking at complex solids made of joined shapes, let's dive into the most important concept for this topic: understanding hidden surfaces. The methodology, Additive CSA. When you have two solids that share a common base, meaning they have the exact same radius, those flat, circular bases effectively cancel each other out from the perspective of surface area. Why? Because, as we just discussed, they are no longer on the outside of the shape. Therefore, to find the total surface area, or TSA, of the combined solid, you don't need the full surface area of each part. Instead, you simply add together the curved surface areas, or CSAs, of the individual components. To make sure you get this right every time, I want you to follow this general step-by-step approach. First, identify your components. Look at the complex object and determine which basic geometric solids, like cones, cylinders, or hemispheres, make up the whole. Second, verify the bases. This is crucial. You must ensure that the solids are joined at faces with the same dimensions. For example, check that they both have the same radius, denoted as r. Third, identify the exposed surfaces. Look closely at the object and recognize that since the bases are hidden, only the curved parts of the solids remain on the exterior. And finally, apply the formula. Simply sum the curved surface areas of the individual parts to get your final answer. Now that we understand the concept of hidden surfaces from our previous slide, let's look at the actual methodology we use to solve these problems. We call this the Additive CSA approach. In the next slide, we are going to put this exact methodology into practice using a detailed example of a toy model. Detailed example, the toy model. Now that we understand the theory of hidden surfaces, let's put it into practice with a detailed example. Imagine we have a toy model, specifically a cone mounted perfectly on top of a hemisphere. Because they fit together perfectly, both shapes share the same base radius, which we will call r for the cone. Let's also denote its slant height as L. Let's break this down step by step using the methodology we just discussed. Step 1, let's analyze the hemisphere. If this hemisphere were sitting by itself, its total surface area would consist of both its curved surface and its flat, circular base. However, remember our rule from the previous slide about hidden surfaces? Since the base of the hemisphere is now joined to the cone, that flat base is no longer exposed to the outside. Therefore, the only part we care about is the curved part. So the exposed area of our hemisphere is simply its curved surface area, which is 2 pi r squared. Step 2, now let's look at the cone. Just like the hemisphere, a standalone cone has a curved surface and a circular base. But once it is glued to the hemisphere, that circular base becomes an internal boundary. It's hidden. This leaves us only with the curved part. So the exposed area of the cone is its curved surface area, which is pi rl. Step 3, now we can calculate the total surface area of the entire toy. Following our additive CSA method, we simply sum these two exposed areas together. The total surface area of the toy equals the curved surface area of the hemisphere plus the curved surface area of the cone. Written as a formula, that is 2 pi r squared plus pi rl. Finally, step 4, if you want to make your calculations cleaner, you can perform an optional simplification. Notice that both terms share common factors. We can factor out pi r from the entire expression. This gives us a much tidier final formula, pi r multiplied by the quantity 2r plus l. As we move to the next slide, keep this specific calculation in mind, as it perfectly illustrates the key takeaways we are about to summarize. Key takeaways. First, always keep an eye out for those hidden faces. As we discussed earlier when looking at the wooden discs, the moment you join two solids together at their bases, those flat surfaces are no longer on the outside. They've become internal boundaries, so they are no longer part of the exterior surface area. Second, this leads to a very important distinction you must make: the difference between CSA and TSA. When you are dealing with combined solids that have matching bases, you should not use the individual total surface areas of the shapes. Instead, you must use the curved surface area, or CSA, of each component. This ensures you aren't accidentally including those hidden, internal bases in your calculation. Finally, let's look at the core logic behind our formula. To find the total surface area of a combined solid, the logic is simply to find the sum of the curved surface areas of all the individual parts. In mathematical terms, the total surface area of the combined solid equals the summation of the curved surface areas of the individual components. All right, let's wrap up what we've learned today by reviewing our key takeaways. Now, before we finish, I want to point out a very common pitfall in the next slide, so pay close attention to how we avoid overcounting. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and highlight a very common pitfall that many students encounter when tackling these types of problems. This is the mistake of adding individual TSAs. It is incredibly tempting, when you see a complex shape, to simply calculate the total surface area of the first solid, then calculate the total surface area of the second solid, and add those two results together. You might be tempted to write down an equation like total surface area of the combined object equals total surface area of solid 1 plus total surface area of solid 2. As we discussed in our previous slides regarding hidden surfaces, this approach is mathematically incorrect. Why is this wrong? Well, if you use this method, you are actually counting the area of the joining faces twice, once as part of the first solid and once as part of the second solid. However, as we learned, those faces are now internal boundaries. They are tucked away inside the object. By including them, you end up with a calculated area that is much larger than the actual exterior surface. So, as you work through your practice problems, I want you to keep this golden rule in mind. If you cannot touch the surface because it has been covered or glued to another part, it is not part of the total surface area. Always focus on the exposed or curved surfaces only.